Hey everyone, welcome to Insights by Irish. In today's video, we are going to make the time series forecasting project using LSTM approach, long short-term memory. And here we are also going to work with multivariate data, which means we will be having more than one column to make the forecast. Now, the purpose behind using the LSTM for time series forecasting is time series data is always sequential in nature. It is always ordered in nature, whereas LSTM is also known to handle the sequential data. Hence, it works really very well with the time series data. Secondly, LSTM is very good in capturing long-term dependencies, which helps us in making the time series forecasting. So the dataset that I am going to use for this particular project is this Apple stock price prediction from Kaggle. I will provide the link of this dataset in the description box, and I have downloaded this dataset and loaded here in the Google Colab environment, as you can see here. So let's start building the project. The first stage that we have here, let me give the heading, is loading the data. So let me import the libraries here, import pandas as PD, and then here I will load the data. So let me say pd.read_csv, and here I will provide the path of dataset. So let's check the dimension of our data frame here. So this data frame in total consists of 251 rows and 7 columns. Let's also display that. So as you can see, this is our data frame df. Date will be our index, and apart from date, all other columns starting from open up till volume will help us making the time series forecast. Fine. So this was the first stage of loading the data. The second stage is data pre-processing. So let me write here data pre-processing. In order to make your data efficient to work with time series model, it's very necessary to perform a lot of pre-processing on that data. So let's start the same. First, we will check for the null values. Let me say df.isAny.sum. This will give us the count of null values from every column. As you can see, for every column the value is 0, which means we don't have any null values in any of the available columns. Second thing, we will check for the data types here. So let me say df.info. So as you can see, here we have the column names, and here we have the data type of all the columns. So the date column here is in the object data type, but when working with time series data, it's mandatory for the date column to be in the date time data type. Hence, next thing that we want to do here is converting the date column into date time data type. Fine. So for that, what we have to do, we will say df, then the column name, which is date, is equal to, then we will make use of pandas here, the to_datetime method from pandas actually. So to_datetime, this is the inbuilt method from pandas, which helps us to convert the data type of any column into datetime. Then pass the column name here again from the data frame df, it's date, and let's run that. Let's again check for the data types here. So as you can see, now the date column has been converted into datetime data type. After doing this, if you see the range index here for 251 entries, that is for all the 251 rows we have in our data frame, we have some random index integers assigned to them starting from 0 up till 250. Next thing that we want to do here is we want to make this date column as our index. We don't want this random integers from 0 to 250 as our indexes. We want this dates to be our new indexes. So let me say here, making the date column as index. So here I will say data frame dot, I will again make use of the inbuilt method, which is set_index. Here we have to pass the column name, which is date, and in order to make this changes permanent, we will say in place is equal to true. Let's run that, and let's again make use of info method here. So now if you see, the date time index has been assigned as our new index. So for 251 entries, we don't have any random integer indexes from 0 to 250, but we have the indexes of date, that is starting from 2018 up till 2019 for 1 year. So after making this index, you can even display the data frame here. Let me say df dot head. So as you can see, now we have this date column as our index. Fine. So this is what we wanted to do. Next, while working with LSTM, as I said previously, we handle the sequential data. Hence, it's also necessary for that data to be in the ascending order, or you can say the sequential order. So you cannot have any dates up and down. You should have them in sequential order. That is, starting from X position, it should always go in an ascending or an descending manner up till its target. Fine. So the next thing that we want to do here is to sort the indexes. So let me say here sorting indexes. So here I will say df dot sort index. Again, this is an inbuilt method here, and here I will just say increase is equal to true in order to make the changes permanent. Let's run that. Fine. So this was just about the sorting the indexes. Now the next thing that we want to do here is to perform data normalization. So let me write here data normalization, and you can perform data normalization using min-max scalar or standard scalar, anything that you want. I am going to use min-max scalar here. So let me go back here and import the library first. I will say import actually from sklearn dot preprocessing. I will import min-max scalar. Let's run that. So let's go back to the data normalization cell, and here what we are going to do, we will create an object of min-max scalar. So scalar is equal to min-max scalar. After that, now we are going to scale the values. So let me write scaled values here. So scaled values is equal to scalar, and we are going to make use of fit underscore transform method, which will directly fit our data and also transform it. So here I will say fit underscore transform, and here I will pass the columns from data frame. So let me say df, and from here I will say df dot columns. So I am going to pass all the columns to this min-max scalar for normalization. Let's run that, and let's display the scalar values here. So let me say scalar values. Let's run that. So as you can see, these are our new normalized values, but right now they are in the array format. So the next thing that we want to do here is to put this data into a data frame format. So let me say here data frame underscore scaled is equal to, so here I will make use of data frame method from pandas. So pd dot data frame, here I will pass the scaled values. Now we are passing the scaled values to be inserted into a column like format, row column format basically, but they also should have some column names. So the column names, we are going to extract it from the original data itself. So let me say here columns is equal to, here we have to specify the column names. So we will say df, which is our original data frame, dot columns. So whatever the column names the original data frame has, the same column names will be given to this particular data frame as well. And after that, here I will say index. Now we also have to specify what index we want to use here. So again I will say here data frame dot index, which means whatever index the original data frame df has, the same index will be given to this particular data frame as well. Fine. Let's run that. It's actually scalar values. Fine. Let's display the data frame now, df scaled. So as you can see, now we have this normalized value in the data frame format. So this is what we wanted to do. Now all this stuff that we did comes under the data pre-processing part. After performing this data pre-processing, the next step that we have to do here is plotting the columns. So let me say here the third stage, which is plotting the columns. Fine. Now as you know, we have more than one column here, that is we are having 6 columns here to be more specific. So we want to plot the data for all the 6 columns. Now what's the reason for plotting the data? By plotting the data, we can analyze whether there is stationarity in the data or not, whether the data is seasonal or not, whether there is any kind of uptrends, downtrends, or any kind of patterns in the data. So it's necessary to plot it. And as we are having more than one column for plotting, we will make use of subplots here from matplotlib. Let me import the matplotlib here. Let me say import matplotlib.pyplot as plt. Let's run that. So coming back to the plotting part, here I will give the figure size first. So let me say plt.rcparams. Here I will specify the figure size. So figure.figsize, and then specify whatever size you want to. So this is purely based on trial and error. Let me say 15,15. Then I have to initialize a subplot here. So let me say figure, axis, plt.subplots. Now we want total 6 plots here. As you know, we are having 6 columns in our data frame, and for that we want 6 subplots. Hence I have specified the value 6 here. After that, let's start plotting. I will create a for loop here. So for x, that is the short form for axis, and col, that is the short form for column, in zip. In zip, now we have to pass the axis, the original axis that we had here, and then the column of scale data frame. So let me say scaled dot columns. Fine. So first I will say x dot plot the data frame underscore scale for the first column. That is, in the first iteration, the first column name will be extracted, and here we will plot the graph, or we can say we are going to plot the chart for the first column. After that, we also have to give some title to that plot. So let me say here x dot set title. Now whatever the column name we have, the same column name we will give as a title. So let me say here column name, and then we don't want any x-axis or y-axis. So actually we want y-axis, but we don't want any x-axis. So I will just switch off the x-axis here. So let me say x dot axis dot x-axis dot set visible, and here I will just say false. Fine. Let's run that. So as you can see, it has given us 6 plots, 6 different plots to be specific. We have for open, high, low, close, adjacent, close, and volume. So if you take the look at all these plots closely, you can analyze some pattern here. The columns, or we can say the charts for the columns starting from open up till adjacent, close are very similar to each other. If you see all these charts for open, high, up till this adjacent, close, they look very similar to each other. The patterns, trends that they hold are similar to each other. Whereas for the column volume, it's very different from the other 5 columns. Here we have very different patterns and very different trends. So this was plotting the data, and from this we can also conclude that this data is not seasonal because we cannot find any seasonal patterns here. Now let me also inform you, when working with ARIMA models for time series forecasting, it's mandatory to convert the data into stationary format. But while working with LSTM models, we don't have any such rules. We can work with any kind of data. Now this was the third step of plotting the data. The next step here, the fourth step, is creating the sliding window sequences. So let me write here, creating the sliding window sequences. Now the sliding window sequences approach is only used when we are working with LSTM model while time series forecasting. This approach actually helps the model to learn from multiple slightly shifted sequences of the past data to predict the future data. Now actually here we have to specify a window size, which is also called as look back period, and the significance of that is, depending upon the window size or depending upon the look back period, we can analyze the number of previous time steps that will be used to forecast the next one. So let me make you understand it through a simple example here. So let's say we have this data here 1, 2, 3 up till 10. Fine. And we have specified our window size, which is also called as look back period. Let's say 3. So which means it will use 3 time steps to predict the 4th one. Let me demonstrate it to you. So for the first iteration or for the first step, what it will do, it will consider the first 3 time steps, 1, 2, 3. And depending upon this past data, it will predict the future data, that is for the fourth data, it will forecast the values. Then in the next step, as the window size is 3, it will now consider the next 3 time steps, which is 2, just a minute, 2, 3, 4. And now it will make predictions for the fifth data using this previous 3 time steps. For the next step, let me say that for the next step, it will make use of 3, 4 and 5. And it will then predict for the next data, which is at 6th. So this is how it's going to work. Whatever window size you give here, that many previous time steps will be considered to predict the next time step. As the window size was 3 years, hence we considered the previous 3 time steps. If we would have been given the window size as 5, then previous 5 time steps would have been considered. Fine. So let's write the function for that. Let me create a new cell here, and here I will say def create sequences or create sequence. In this create sequence, I will have the data, which will be my scale data frame, and then the window size. Now in this function, you will create 2 empty lists. One is X and another one is Y. In the X list, you will append the sequence of data, and in the Y, you will append the target data. Then after that, we will write a for loop here. So for I in range, window size, up till the length of data. In X, I will append the data dot iloc, this is the location of index, from I minus window size up till I dot values. Fine. So in this X list, we will append the sequence of data starting from I minus window size up till I, and then in Y, we will append the values. So let me say append the data dot I location of I dot values. Fine. So after appending this data in the X and Y, then we will return it. So let me say here return np dot array. We are returning it in the array format, and for that we require numpy. So let me import that first. So here I will say import numpy as np. Let's run that. So going back to the function here I will return the X in the array format as well as the Y in the array format. So let me say np dot array of Y. Let's run that. And let us now create the sequences here. So we will say X comma Y, and here we will call the function which is create sequence. Now in this function, we will pass the data. The first argument is data, which will be our scale data frame. So df underscore scaled, and then the window size, whatever window size you want to specify, you can specify that before calling this function. So here let me specify the window size first. So I will consider my window size as 60. Now as you know, here we have a lot of data and 6 columns. So the window size should be large enough to create that many sequences. So the window size is 60, and we will pass that window size here. Let's run that, and let's check the shape of our X and Y. So X dot shape and Y dot shape. Let's run that. So let me display X. Fine. So this is the X, and let me also display Y. So one thing you can observe that here we just have 2 lists, but here we have 3 lists, and what that means is here we are having a single list is of 60 sequences. Fine. So let me delete these rows. Now after doing this, next we have to perform train test split. So the next step that we have here, I think it's step number 5. Let me write here, 5th step is train test split. Now here let me say X train, X test, then Y train and Y test. For this we require the train test split module from scikit-learn. Let's import that first. So here I will say from sklearn.model selection, I will import train test split. Let's run that. So here we will call that module, which is train test split. In this module we will pass our x and y, then the test size. You can specify test size as per your choice. I will keep it 0.2, which means 80% data in the training set and 20% in the testing set. Then the random state, which is 42. Then we'll also check the shape of that. So x train dot shape and x test dot shape. Let's run that. So out of 191 rows, now 152 rows are present in the training set, while the remaining 39 rows are present in the testing set. So we are done with train test split. Now the thing that we have to do here is we have to actually build the LSTM model. So let me write here. The next step, which is the sixth step, is building LSTM model. Now for this we require Keras library. So let me go back to the initial cell, and here I will say from TensorFlow I will import Keras. Let's run that. Now going back to the building part, here I will say model is equal to Keras dot sequential. We will be building the sequential model that will execute all the steps in a sequential manner. In this, we can add n number of LSTM layers as well as the dense layers. So the choice of LSTM layers and the choice of dense layers depends fully upon you. Here I will be adding 3 LSTM layers and 1 dense output layer. So first, let me say here, adding the first LSTM layer. Also, we are going to add the dropout layer for regularization purpose. So here I will say Keras dot layers dot LSTM. Now in this LSTM you also have to specify the units, the number of neurons you want in a single LSTM layer. So you can, again, that's a hyperparameter, you can give any number. I will keep it as 50. Then the return sequence. So return sequences. Now whenever you are going to add one more LSTM layer after the current one, you have to give your return sequences as true. But if that's your last LSTM layer, which means you don't want to add any further more LSTM layer after the current one, then you have to make the return sequences false. So here we are going to add one more LSTM layer after this current one, hence the return sequence will be true. Then you have to give the input shape here. Now in input shape you can either directly specify the values that you can see here, or one thing you can do, which is x underscore train dot shape at index 1 and then x underscore train dot shape at index 2. Now what do we mean by that? You can even copy it from here and you can see what the values are. Let me display it for you. So 60,6 in our input we are having 60 combinations and we have 6 columns. Fine. So this is the shape that we are supplying it here. You can either directly specify 60,6 or you can go ahead with this particular method. So this was the first LSTM layer. Now after this, before adding the next LSTM layer, we are going to add an intermediate dropout layer to handle the overfitting phenomena. So let me say here Keras dot layers dot dropout. This layer will help us manage the overfitting. So you can specify any dropout rate here. Let it be to 0.3, which means from every LSTM layer it will switch off random 30% of neurons so that the model can randomize. Fine. So this was the first combination of LSTM layer as well as the dropout layer. We are going to create 2 more such combinations. So let me copy it from here. So 1 and 2. So in such a way we are going to add 3 LSTM layers along with 3 dropout layers. So this one is the second and this one is the third. And then in the second and the third layer you don't have to specify your input shape. It's just in the first layer. Now after that, the return sequence will again be true for the second LSTM layer because we are going to add one more LSTM layer after that second one. But in the last LSTM layer, that is the third one, we are not going to add any more LSTM layers after this. Hence the return sequence will be false. And the dropout layer and the number of units will remain same for all the LSTM layers available here. Fine. So this was the combination of 3 LSTM layers and dropout layers. After this, we are going to add our final output layer. So let me say here, adding output layer. So the output layer will always be a fully connected dense network. So let me say here keras dot layers dot dense. Now here you have to specify your output neurons. So here we will say y underscore train dot shape at 1. Even see what this means. Let me copy it from here and let me display what's the value of that. You can say 6, which means we are having 6 columns. So that will be our output shape. Fine. So this was the model. Let's run that. It's actually dot here, not comma. Everywhere, let me make it dot. Fine. Let's run that. So after building this model, ignore these warnings, they are none of our use. Then we have to write the code for compilation. So let me write here compilation. Here I will say model.compile. Then we have to provide the optimizer here. So optimizer, let me say it as Adam. Then we also have to specify the loss function. So here the loss function will be mean squared error. So I will say mean squared error. And then you also have to specify your metrics, that is on what basis you are going to evaluate your model upon. So the metrics here will be root mean squared error, that is RMSE. So let me write here root mean squared error. Fine. So this was the code for compilation. Let's run that. After doing that, we now want to fit the model, but before doing that, we are going to add a early stopping condition. Now what this early stopping basically does is, when you specify large number of epochs while training, then it checks for consecutive validation loss. If for a consecutive epochs the validation loss doesn't change, then it automatically abrupts the training process. It automatically stops the training process for you because the validation loss is not changing, which means the model is not learning anymore further, and hence it stops the training process. So we will be adding the early stopping condition here. Now again we have to import the early stopping module from TensorFlow. So let me go back to the initial cell and import that. Here I will say from TensorFlow dot keras dot callbacks. I will import the early stopping. Let's run that. So let's go back to the early stopping code. Here what I will do is I will say early stopping, a variable, you can name it anything. Then I will load the module that we imported. So early stopping. Here we have to specify the argument monitor, that is what we are monitoring. Like you can specify whatever parameter you want to monitor upon. So here we are monitoring the validation loss. As I said previously, we will be observing that if the validation loss doesn't change for consecutive epochs, that is consecutive n number of epochs, then we will stop the training process. So we are monitoring the validation loss. After that, you also have to specify the patience level. Now, as I said previously, it will check for consecutive n steps. So we have to specify this n. N is nothing but our patience. That is, if we want to monitor the validation loss for consecutive 2 steps, then the patience will be 2. If we want to monitor the validation loss for consecutive 10 steps, then the patience will be 10. So here in the same way I will keep the patience as 10, which means this early stopping condition will monitor the validation loss, and if in case it finds that for the consecutive 10 epochs the validation loss is not changing, then it will stop the training process. And then one more parameter that we have to add here is restore best weights. Fine, which is true. So this was the early stopping code. Let's run that. After writing this, now we will fit our model. Let's keep it in a variable as history. You can name it anything. Then model.fit. You can even name it as LSTM model is equal to model.fit, and here we will be passing our training set. So X train, Y train. After this, we have to do validation split here, because as we want to validate or as we want to monitor the validation loss, first we require validation loss for that, and we will have that validation loss only if we have an validation set here. But in this case, we just have the training and testing set. We don't have any kind of validation set. Hence, we have to perform validation split here. So validation split, let's say here 0.2. So the validation split just will be of 0.2. Then we have to specify the number of epochs. Now, as we have given the early stopping condition, we can keep the size of epochs as large. Let's keep it as 100. It won't run for all 100 epochs because the early stopping condition would get involved. Then after that, let's give the batch size. Now, depending upon the batch size, your accuracy or your forecasting changes. So this batch size is again kind of hyperparameter. Depending upon my observation, when you reduce the batch size, you get more accurate output, whereas where you increase the batch size, your output somewhat slightly gets different. So I will keep the batch size as 3, which is lower, and then callbacks. In this callbacks, we have to pass this early stopping code. So here I will pass early stopping. Let's run this. So as you can see, the training process has started. Let's see for how many epochs it happens, because it's for sure that it won't happen for all 100 epochs. The early stopping condition would get involved somewhere here. If you don't put the early stopping condition, then you have to give your size of epochs very small, like 5, 10. But if you are giving the early stopping condition, then you can keep your epochs as large. So the training process is completed. Let's see at what epoch it has stopped. If you check that, it has stopped at 51st epoch, which means the training process didn't happen for all 100 epochs. It got ended at the 51st epoch, and this is because we inserted the early stopping condition. So this is how early stopping works. Now, it might have monitored the consecutive 10 epochs here, and it would have observed that for the 10 consecutive epochs, the validation loss is not changing much. It's actually equal to each other, or either it is very slightly close to each other, which means the training is not happening properly, and hence it ended the training process at the 51st epoch itself. Fine. So after training this, now next we have to forecast the data, for which we might require predictions. So first step here is to make the predictions. So let's say predictions. Now in this predictions, I will say model dot predict, and here I will pass the X test. Let's run that. So the predictions have been completed. Now, one thing you can also do before making these predictions, you can even check any kind of data if you want to see of this LSTM model. So let's use this variable LSTM model, and then you can see all of this stuff on that model. So whatever the parameters are, or whatever the number of epochs, history, model, all those stuff. Let me say your history. It will give you all the errors, validation loss, root mean squared error, everything, right? So you can see any data about the model that you have recently trained. Fine. Let me hide this output here. So after making the predictions, now we can go ahead for making forecasting. So let me write here the next step we have. I think this is the 6th step. Let me confirm. No, it's actually 7th. So the 7th step that we have here is forecasting the data. Now, to forecast the data, first we have to perform inverse scaling, and that is because right now whatever values we have are in the normalized form. As you know, we have performed min-max scaling here. So whatever data that we are having is in the 0 to 1 range. Fine. So inverse scaling, what it basically does, it reconverts your data back to the original form. So let me write here inverse scaling. Because if you don't do this inverse scaling, your forecasted values won't match with the original values, because original values would be on the normal range, but your forecasted values would be on the 0 to 1 range. Hence, it won't match. So inverse scaling, here I will say predictions, because even if you check the predictions here, let me say predictions, the first 10 predictions. It's actually predictions. So you can see they are in the decimal format. Hence we are performing inverse scaling here. So here I will say predictions is equal to scalar. This scalar is the object in which we have loaded our min-max scalar module, and here we will use an inbuilt method which is inverse underscore transform. This is inverse transform, and here we will pass the previous predictions. So let me copy it from here and paste it here. Now these predictions are the previous predictions that we performed here, and this prediction is the new prediction variable with the same name. Fine. And we also have to perform inverse scaling on the y-test data, because the y-test data, even that is in the normalized form. So we will say y-test rescaled, and we will say scalar dot inverse transform. Here we will pass the y-test. Fine. Let's run that. And now if you check the predictions for the first 10, let me say here predictions for the first 10 data. So now you can see they are no longer in the 0 to 1 range. Fine. Now after performing this inverse scaling, you can go ahead for plotting the results. So let me say here plotting the results. Now we will plot the results in a different manner. Like initially what we did here, we tried to plot all the plots consecutively one after the other. Here we will try to plot the results for all the columns and using the subplots basically. So let me say here plt dot figure, then give the fixed size whatever you want. Now as we are going to plot this particular plots, and not only one after other but also in the column row format, hence we have to give a small figure size. So we will say 14,7. Then let's write a for loop here. So for I comma column and enumerate. Now here we have to pass the columns of our data frame, which is scale data frame. So let me say here df underscore scaled dot columns. Now in this for loop, first I will try to plot the subplot here. So let me say plt dot subplot. Here I will say 2, 3, I plus 1. Now 2 basically I want 2 rows and 3 means I want 3 columns. Fine. After that I will say plt dot plot. Here I will pass the y-test rescale, not the original y-test but the rescaled y-test. So let me copy it from here, starting from till the ith location. Fine. After that, let's give the color as blue so that we can distinguish between the actual values and the predicted ones. Then the label. The label will be actual and then the column name. Fine. So this was the plot for the actual data. Let's try to build same plot for the predicted data as well. So let me say here plt.plot. In this I will pass these predictions. Now these predictions are the inversed one. So let me copy it from here. Then again the same thing up till I location. After that, let's give the color for the forecasted values as red, and then the label as predicted, or you can say forecasted as well. So let me say it as predicted columns. So whatever that column name is, that we will pass it here. After that, we also have to give the title to our charts. So let me say plt.title. The title will be the column name itself. So let me say column name and price prediction, or instead of price prediction you can just say here prediction. After that, let's give the x label and y labels. So let me say plt.x label. Now in this x label we will have time, and in the y label we will have the price. So let me say here whatever the column is and price, and we also have to add the legends here. So let me say legend. Let's run this. Just a minute. It's actually fixed size. I missed S. So as you can see, this is your final output. If you take a closer look at every plot, you can see the red line signifies your predicted values while the blue line signifies your actual values. And for every plot except for the volume, all the predicted values are exactly matching or very closely matching with the actual ones. So as you can see, there is a slight overlapping of the second row on the first one. So let me do something like this here. I will say plt.tight_layout. Let's run that again. So now you can see we don't have any more overlapping here, and you can see all the plots. Let me zoom in for you. So you can see these red lines are your predicted values. At some places there is a slight difference, while at other places they are exactly matching with the original ones. Now you can see for all the columns from open up till the adjacent close, the predicted values are matching with the actual ones. That is, the model is performing well for all these columns. But for the volume column, it's only capturing the trends but not the exact pattern, or not the exact values, I can say, because wherever there is uptrend in the original data, even the predicted value shows the uptrend. Wherever there is downtrend in the original data, even the predicted values are showing the downtrend, but the exact data is not getting captured, just the trends are getting captured. This is because even if you see the original plot here, you can see the volume column is different from all others. Here you can see the volume, the data for the volume column is very different from all other columns because there is a lot of variance here. Fine. So apart from that, all other column is doing really well and the model is performing efficiently. Fine. So this was the project of performing time series forecasting using LSTM and also with the help of multivariate data. So that's it for the video. Thanks for watching.